Good afternoon. Can you guys hear me okay? Can you guys hear me okay?
Yes, sir.
Okay. Okay. So let me start the recording. Okay. So any questions from previous lecture? All right. So what we plan to do is I will be finishing the process management today, right? We have about 14 slides left. So I'll be finishing the process management today, and that will be up to, the process management will be the course in the exam, right? So we have covered the shell scripting, we have covered the basic C programming, the revision of C programming. Then we have covered the GCC steps and libraries and make files and things like that. Then we have covered file IO, and we have covered the process management, right? So these are the topics that we have covered till now, and these will be the topics that will be there in the exam syllabus. Okay. So process management will be the last topic. I may start a new new topic after this one if we have time, but we'll basically have in the exam syllabus we'll have up to the process management. Okay, so in the previous lecture we considered, or we were reviewing the exec system call, right? So what the exec system call does, it allows us to run a different program, right, different application, either in your child process or the parent process, right? Basically there are 4 flavors of exec system call. In the first flavor, what we have to provide is the program name, including the full path of the program, and then we have to provide the command line argument in the form of individual values, right? So we basically provide a list of arguments. That's why the L is there. So L stands for the list, and once you have provided all the arguments, to say that there are no more arguments for this program, then you provide a null value. So this null value indicates end of the list, right? That is what we provide. In case of the V format, right? So we have exec V format. In the V format, we provide the command line arguments in the form of vector, and this vector is for string, right? So you have multiple strings, which is an array of string, right? So that is how we provide an argument. So therefore there is no null at the at the end, right? So again, here you are going to provide the full path with the application name or executable file name, and you are going to provide an array with command line arguments. So these two flavors of exec call is repeated here, except that there is this P at the end, right? The P at the end. And what that P stands for is that the application name that you provide doesn't have to have a full path provided. Why? Because the P version of the exec call expects that the application executable file name that you have provided is available in one of the directories, one of the folders that are in the path environment variable. right? So we know that in the path environment variable, when you look at the path environment variable, it has a list of directories, list of folder names, right? So this exec system call will be expecting that your executable file name that you want to run is part of one of these folders, So that is what the flavors, different flavors of exec call do. Okay. So again, the one with the P expects that your executable file name is somewhere in the path environment variable, and therefore you don't have to provide the full path. In the L format, you have to provide the list of command line arguments with the null as the terminating argument value, and then the V format allows you to provide the command line argument in the vector format or a array format. Okay. Now what we are going to do is, so that is what the explanation in this slide is. So now what we are going to do is we are just going to run a basic basic code that just shows you how we can use the exec call in the program. Now here you can see that I don't even have a fork. Okay. Why? Because we are just, what we are doing is whatever is this code here, we are just replacing this code with the code of the ls command. Okay, so we know that ls command is there in the in the folder, the path environment variable, but purposefully I'm using the version of the exec call without a p part, right? So if I would have done p, then I can just provide here ls, but since I have not done p, I have to provide a fully qualified path, which is basically /bin/ls. Okay, so what will happen? It will basically start with the process, my original process, to print this line. Then when I execute an exec system call, it will replace the image, the memory image for this process using this code. So whatever is the current executable code which is there in the memory for this particular process will be overwritten by the code of the ls application, ls executable. Okay, and therefore any line that you put after the exec call, will not be executed. Why it will not be executed? Because you have already replaced the memory, the code memory and the data memory with your ls command executable file, executable code, right? So therefore this line actually does not even exist in the memory anymore. That line or this piece of code is overwritten by this piece of code. Okay, so here we have just replaced the original program, original process with the code of ls. Okay, and so this line will be printed yes, and then it will immediately start running the ls command, and then this line will never be reached or will never be executed because that code no longer is available in the memory. Okay, so let me show you an execution of that program so you know how it works. Okay, so now if you go up here, you see that this first printf is printed from our code, from our application code, right? And it is saying that I'm a process ID so and so, and I am about to execute ls-l, right? So that printf is coming from here, right? And then the ls command gets executed, and so you see that this output is coming from the ls command, right? And then finally this particular printf is never shown, it never appears. Why? Because again, like I said, the process memory for the code and data is replaced by this particular program, this particular binary, right? So our binary of this particular program, this executable, which is the exact example executable, is actually overwritten by the ls executable. So therefore this line itself is not there in the memory. In fact, none of this code is there in the memory, right? So that's why it's not going to be able to run that printf. Okay, but this is not an example we want to see. It's a dumb example in a way, right? Because we are just replacing our own code with ls code. The idea behind using the exec is generally you want to distribute the work in the child processes, and the child process does something right, which the parent process wants to be done by multiple processes. So the basic idea is that how would you run a different program in a child process and a different program or different code in a parent process, right? So that's where we do the fork, right? So in this example, what we have done the fork, and then fork, it returns 0, which means that this is the child process. So in the child process, we are going to run a different program. Okay, so you see that here we are using a V format and a P format. So what is a V format? V format means that we have to provide the command line argument as a vector, as an array. Okay, so you can see that in this particular, our own application code, we will pass the first command line argument as a program name. So for example, if you want to run an ls command, the first argument value will be a ls. And then subsequently in argv2, argv3, and so on, we can provide additional argument for that program, for that application. Okay, so for example, when you run ls minus l or ls minus ltr, so those minus ltr option comes into this program as argv2. Okay, but when you look at the actual program that when you run, like for example, when you run an ls code, right? In the ls code, always remember that, so let me actually draw you a picture a little bit. One second. Let me connect the okay. Okay. So basically, let's assume that my application code is called a.out. Okay, a.out, right? And so this is my argv vector or array, right? So I have a 0th location, I have the first index, I have a second index, third index, and so on. So for this particular application, for my own application, a.out will be at index 0. Then ls will be the argument that I'm providing as a command line argument to this program. So my index 1 will contain ls, right? Argument 2 will contain, let's say, minus l or minus ltr, whatever the option I have provided for the ls program to run. So this is what my argv array will look like. But when you go to run an ls command, right, for this particular program as a child process in my exec, so from here I am basically running this in the exec. I'm using an exec to run an ls command. So when I look at my array here, what this array should look like? So at the index 0, it should actually have ls here. At index 1, it should contain minus l. What it means is that if let's say this is the address 1000, this is the address 1000, let me call 1004, and this is the address, let's say 1008, whatever, right? So I'm just giving some memory addresses here, right? Then actually this value is referring to this address, right? This value is referring to this address, which means whatever is the data at this address should become my 0th index. So should be my first element in the array, in the argv array here. So this is the argv array for my ls command. What it means is that whatever is the address of the first argument, whatever is the address of the first, index 1 value in my a.out should be provided as an address of my argv0 here, or the array of the command line argument here, right? What does that mean? It means I have to say address of argv of 1. That is what I need to do. So when I use this one in my this code, which means I'm providing this address as the command line argument for this particular program. And if you look at the code, right? If you look at the code, that is what I'm doing here. Okay, so we are saying that LSCC program we want to run, let's say for example, and then here I'm going to provide the address of the first first index, which is actually the argv0 for my child application, or the application that runs in the child process. That is what we need to do here. Okay, so this is how my child process is going to take whichever program that I pass here and run it here. So again, if we run this process, or if we run this code, run exec in child, right? And let me run ls minus ltr. Okay, so now you will see that the parent process says, in this case, there is nothing to be done here. Why? Because if you look at the code, this is my parent, right? And in the parent, there is really nothing to be done unless I could put the wait code here. I can put the wait here, and maybe parent can actually wait for the child process to finish. I can do that, okay? But in this particular example, I didn't do it because really parent does not have to wait for the child process, okay? So therefore, I didn't put the wait. And then in the child, we passed the ls command, right? So we pass the ls command with the option of ls minus ltr. And therefore, if you see this, it is actually printing this particular value. Okay. I could run a different program also. It doesn't have to be always ls. So let's say I can run ps minus ajxf. I can run that command also. So you see that as a child process, it is running a ps command. Okay. So in short, any application you want to run as part of child process, you can provide as a parameter over here. Okay, and you can run that. So this is how you can run a different program in the child process. Now, why we are learning this, right? So the question is why we are learning this. The reason we are learning it is because we want to actually distribute the work that we want to do in multiple child processes. So if you recall, I had mentioned earlier that it is not always necessary that you have a single child process for a parent. It is definitely possible that you have more than one child processes, and each of the child processes may run different applications and do different work, or maybe it runs the same application but it accepts different data as an input, right? And then it performs different work because the data is different, program is the same but different data. So it is the same application code but runs on a different program, different data, right? Or you can run different application code in a different child processes. Either way you want to do, you can actually implement this master slave implementation. Okay, so let us look at how do we do master slave implementation. So let us first look at the child code, right? So this is my child process code, and it is a very simple code. You can see all it is doing, it is accepting two command line arguments, argv1 and argv2. I am assuming that the command line arguments are a numeric value, and so using A2I function, A2I system call, we are converting this ASCII value into an integer value. So we are assuming that the value that is being passed over here is an integer value. So I get two different values, num1 and num2, from the two arguments that are passed, command line arguments that are passed. I sum them up, I print this message over here from the child, and then I exit, but the exit code which is returned back is the sum of these two numbers. Okay, so sum of these two numbers are passed back to the parent. So when you do exit, basically we have seen, if you recall, I had shown you an example of the code where you can actually read the exit status in the parent process for the child, right? So for each of the child, whatever the sum value is being exited back, as an exit code, that can be read by the parent process. Okay. The only condition is this has to be a single byte value, single byte integer, positive integer value. That is the only condition. So as long as it is the value between 0 and 255, then you can actually return that value back. Now, if you run this application code, it doesn't actually require the parent. So I can actually run the child process as is. Okay. So let me do that. So it's process child dot out, and let me provide two values, let's say 10 and 20, and you will see that it tells me that I am the child process with the PID of this one, and I got the two different values, 10 and 20, as the command line arguments, and then the summation of that is over here, right? So these are the two printfs that are there in this child process we have done. One coming from here, where we are printing the process ID, and then here we are just printing the summation value. Okay, so the child process, the application code that we have written as a child process is actually a separate C code, completely separate C code, and it is not dependent on any other parent, any parent code, right? So it is a completely separate executable file, completely a separate C file. It has no direct connection with the parent program. However, when you go to the parent code, right, in the parent code, what we are expecting is that in the parent code, we are going to provide multiple, multiples of two numbers as a command line argument. So the way we will run the program will be the program name or the application name, which is the parent process.out, and then we will have num1, num2, num3, num4, num5, num6, and so on, right? So num1 and num2 will be provided as an argument to child 1. Num3, num4 will be provided as an argument to child 2, right? Num5, num6 will be provided as argument to child 3, and so on. Okay. Now, what we do is we figure out how many child processes we need to create using this fork, this for loop, right? So we say, let's say that argc value will be 7 or odd number, because it also includes the argv0. Okay, so argc also counts argv0, which is actually not useful for us. So all we need is argv1 and all the way up to whatever argvn is. But we are expecting that the value is multiple of 2. We have not checked it here, but you can also do that validation. Okay, you can do the validation to check that argc is always the odd number value, so that we always have the even number of numeric values that are being passed. Also, we have not checked that these numbers has to be numeric, but again, all those validations can be done in the code, right? So what we do is that using this for loop, we are saying that how many child processes are needed, right? So we are saying go from 0, argc minus 1, and I equal to I plus 2. The other way you can do also is that argc minus 1 divided by 2. I mean, either way, right? And then you can just increment the value of I. So either way, you can do all those things, right? But so this is how we are running the loop. Now within the loop, you can see that we are creating fork, right? We are basically creating a child process. And in the child process, we are saying what are the arguments that we are going to pass to that child process. So always, if the I value is 0, that means it is my child 1, right? The first child. If the if the I value is if the I value is 2, that means it is my child number 2. If the I value is 4, then it is my child number 3, and so on. So what we are going to do is here we are going to say I plus 1 and I plus 2. These are the two arguments we are going to pass. So in the child process, we are always going to get 1 and 2, 3 and 4, 5 and 6, and so on. And here we are using the exec L, which is the list format, right? So in the list format, what do? we provide the executable name, right, as the program that we want to run. And then this is my argv0 value. Okay, so argv0 also is the same as the program name, right? That is what we said. That is the example that I was showing you here. So let's say here should be my executable name of my child process. And then all the parameters that I am passing over here from argv1, argv2, and so on, right? So that is what my argv1 will be here, and my argv2 will be here. And I don't have any more parameters, so I'm just going to put the null. So when I do this, the child process, my child process, the executable file that I have here, this code will be executing using my exec command. And each time when this exec command will run in this for loop, right, in this for loop, each time a new fork will be done. The new fork will create a new child process. And in each of those child processes, my process underscore child.out will get executed. Now you will ask me the question that why this, why this fork will not get executed in the child process and it is only executed in the parent process. The reason being that, one second, I think somebody's working here, so I'm just going to use the headphone. Are you getting a background noise? Are you guys getting a background noise?
Somewhat, yes.
One second. So let me just use the headphone. Okay. So basically, as I was saying, see, when you do exec, we said that we replace the code and the data area in the memory from this code, from this particular application code to the application code which is for this program, which means that all the child processes that we are creating are never going to go back into the for loop again, right? It is never going to go back into the for loop again. Why? Because as soon as the child process reaches here, the code and the data will be replaced by the child process's application code and data. So it will start basically putting the code of this one, and that the code of this particular process will be replaced. Okay, so the child process will never execute fork again. Only the parent process will fall off from this if statement because the condition for the parent process will be false. And each time when it comes out of the if, it will again go back to the for. And in the next iteration, again that parent process will execute the fork. A new child process will be created. Again, that child process will start executing this code and the parent will fall off again from the if. Again, it will go back up. So what I'm trying to say is that the iteration of the for loop will be executed only by the parent process and not by the child process. Because every time when the child process comes here, the condition will be true, and therefore this particular application code will be replaced by this particular application code. Is that clear to everyone? I mean, you have to imagine the memory map in your mind because it's not very I mean, I can draw a little bit here, but unless you can envision it, it will not be very easy to understand, right? Okay, so this is how the child processes will be created. Okay, this is how the child processes will be created. Now, once the child processes are created and once the child processes are passed this argument, we want the parent process to wait for all the child processes. Okay, so one option we had earlier was to put that wait in the else part. But the problem there is if you put the else in the if you put the wait in the else part, what will happen? The first time when we go inside the for loop, the child process will go in this if part, the parent process will go in the else part, and immediately the parent process will be waiting for this child process which is just created, which means that until that first child process that was created finishes or terminates, the parent process will not come out of the wait mode. And therefore, once that child is terminated, the parent process will come out of the wait, it will do all that, again it will go back into the iteration, and then the second child process will be created, and then again it will wait for the second child, right? So you see what is happening. It is not actually, we are not creating multiple child processes at the same time. We are actually creating child processes sequentially, because every child process, when it is created, a parent process has to wait for that child process, which is not the way we want, right? The way we want is, we want to fork all the child processes at the same time, and then whichever child process finishes, we want to wait for all those child processes later, right? So what we have done is, we have not used the wait in this else part, right? I have commented these lines out. Instead, we have created a new for loop here, and therefore what will happen is, this for loop, the first for loop will be executed by the parent process. All the forks will be done, right? So whatever number of child processes we need will be created here, right? And all those child processes will start running. Then once this the first loop is done, right? The first for loop is done, then only the parent process will fall down here, because we know that all the child processes will start executing only this code, right? So child process will never come over here. Only the parent process will come here. And once the parent process comes here, then we put a wait loop, right? So again, we are saying how many child we have created. For the same number of child, we are going to issue that many number of waits. Okay, so here what will happen is, while we are waiting for the child process, it could be any one of the child process that could finish first, and then the parent process will come out, right? And then when the next child process finish, again the parent process will come out, because we are waiting for that many waits, right? We are doing, let's say if you have 3 child processes, then the 3 times the wait system call will be issued by the parent. Okay, so for each of the child, we have that many wait will be executed, and for each of the child, we basically get the exit code, right? The exit status code, which is the value, which is the sum value that is going to be sent back using an exit command from the child process. Okay, so this is how you can actually implement. So this is my master, right? My main program, my master program, and this is the task that I want to do as a child. Okay, this is the task I want to do as a child, and this is my master. So let me execute this code and show you how it works. So let me pass the value as 10, 20, 30, 40, 50, and 60, right? So I'm basically supposed to be getting 3 child processes starting together, right? And then the parent process is supposed to be waiting for all the 3 child, and whenever the exit code comes back, whenever the child terminates, it is supposed to display the sum of coming from each child, right? So you see that these child processes started, right? So the first child process is 4220, then 4222, and then 4221. So you see that this child process is actually is created as a second child process, and this is actually a third child process, but the third child process started earlier than the second child process. So it can happen like that, right? Because we are running all in concurrent mode, right? We are running all the processes in concurrent mode. Okay, and then your child finishes in a certain order, and so the parent process is printing that output. If I run this multiple times, you will see a different sequence every time. you will see a different sequence. So here you can see now the second child comes here, third child comes here, and then the first child comes here. Okay, this is the first child, this is the second child, and this is the third child, something like that, right? So what I'm trying to say is that every time when you run, you will probably see a different order in which the printf statements are being executed. The reason being that all the child process and the parent process, all of them are running simultaneously. Okay, and parent process is waiting for each child after starting all the child processes, not waiting for individual child at a time, right? Now if you if I change this code, right, and if I comment this line out, if I comment my for here, and instead I keep my else part, right? So instead, if I keep my else part, okay, now you will notice, if I have to recompile it, now if I run this code again, every time you will see exactly the same output, and it will always be that the first child finishes first, second finishes second, and third finishes third. Every single time, you will not see much of the change in the output, right? You will not see much of the change in the output. The reason being that, like I said, the parent process has to wait for this child to finish. Then only it is going in the second iteration, and it is starting the second child. Then it is waiting for the third iteration or second child to finish, and then it goes into the iteration again and starts the third child, and so on, right? So therefore, make sure that when you implement a parent-child relationship like this, if you have multiple child processes, don't implement it like this. Because if you implement it like this, that means even though you think that you are running multiple child at the same time, you are really not. Right? You are not really running all the child at the same time. You can only do that when you do this for here and not using this else part. Okay, please make sure you understand that very clearly. Any questions? No questions? Okay. So we have used fork, exec, and wait call so far. So if you have to implement all the three at the same time, meaning that you just want to run one particular different program in your parent process, then there is a simpler version of all these three combined system call in system, right? So system is a system call which will basically accept your program name as a parameter, and that it will run by using fork, exec, and wait, right? So you don't have to actually do you don't have to issue these three different calls differently in your parent process. All you have to do is system, and then that's it, right? So again, not very frequently this will be used, but this functionality is available to you in case if you want to use it. Now, we have seen that a lot of processes are created by us when you execute an application or run a GUI application or whatever. But how does operating system keeps track of information about the processes, right? So obviously one area that we know of is the PCB. Okay, but there are certain information which it has to keep track of and has to be stored in the disk. Okay, and what it does is there is a directory in your Ubuntu based environment, and that directory is called proc directory. So let me just open a new terminal window and cd/proc. Okay, so you will see that there is in this directory there are a lot of directories with these numbers, and these numbers are nothing but the directory with the process IDs. So if you do ps minus ajxf, you will find that these numbers, right, these process id numbers, for each one of them there will be a directory in my proc directory. Okay, so each one of those directories will be having each of those process id will be having a directory here. Now how do I know that? So what I can do is I can open a browser window, for example. Okay, I can open a browser window, for example, and then I can run ps minus ajxf and then grep Firefox. So Firefox is the application which is supposed to be running, right? So you see that I have this Firefox application running, right? And I have these process IDs which are related to the Firefox. Okay, so let's say if I pick, let's say this particular process ID 4445. Okay, and if I do cd 4445, and you will find a directory with that ID. Okay, so when you look at this directory, it will have certain other subdirectories or files, and it will have some important information about that particular process. So it will tell you that what are the memory maps, or what are the memory locations that this application, this process is using, what are the different file descriptors it is using. So let's say if I go to fd and if I do ls, it will tell you all the different file descriptors that it is using over here, right? So these are all the file descriptors it is using. It may have an information about the mounts, different file system mounts. It will have an information about the environment variables. There was somewhere env. Let me just do get env environment, right? So you can see that this environment file has the environment variable list information. If you say status file has the information about the status of the processes, whether the process is sleeping, what is the process ID, what is the parent's process ID, which are the user ID who owns the process, and so on. Like a lot of information is provided over here, right? It also provides how many times the process has context switched, right? Voluntary context switching, non-voluntary. So non-voluntary is basically your processor has told the process to switch, right? Context switch, right? Whereas this one is where, let's say there is some IO activity or some activity that was going on. So therefore the process has to go into the sleep mode because some major IO activity is supposed to be happening, right? Which CPUs are allocated to the process, what memory area is allocated to the process. All of that information you can actually find from from the directories here. Okay, so if you look at the next few slides, I got some of the information from this link here, kernel.org, where they have provided this proc.txt, and that proc.txt tells you that which of these files has what kind of information. So basically I've collected that data from there, and I've provided that information to you here. So again, this is something that we may not use on a day-to-day basis, but as a system programmer, we should be aware, or we should know that how Unix-based operating system keeps track of information for different processes. Okay. All right. Now we have used environment variables as part of the shell scripting, right? But very few people actually know and use environment variables as part of C programs. So if you want to have an access to the environment variables in C program, it is definitely available. Okay. However, you may not be aware of it. So what we will do is that first we will see this part. So let me just go to the code here and show you. So normally we are used to only declare main function using these two variables or these two arguments. argc tells you the number of command line arguments, or count of the command line arguments, and this is where the actual values are, right, in this array. However, there is a third array which you can also use in the main function, and this array of string is nothing but the environment variables that are accessible or available in your C program. Okay, so whenever you run your C program from the terminal window, whatever environment variables are available on that terminal window, all of those are also available in your C program, and you can actually access them using this particular array. So in this program, all simply we are trying to do is we are trying to read each string from this array, and we are just printing that string, which will basically have nothing but the strings of environment variables. Okay. So if I do close this one, close that one. If I do env is another, we know that it is a shell command that prints the list of environment variables, right? So these are all the environment variables we have in this terminal window. Okay. Now, if I run my application code, which is display environment varies, right, I am expecting to have exactly the same output, right? So you see that this is where I ran the program. I ran my application, and you will notice that the list of environment variables are going to be exactly the same as the list of environment variables that you get over here. Okay. So in short, what I'm trying to say is that whatever you have available in the shell window as an environment variable, the same environment variables are also available in your C program. Okay. Similarly, in the shell terminal window, we do access a particular variable. So for example, you can say echo $home, right, and it will display the value of the home environment variable, right? Or you say echo $path, it will display the value of path environment variable. You can also set the environment variable using export command, right? So you can say export, and then let's say course equal to sys soft, whatever, right? So you can set your environment variable as well, right? Now you are setting this environment variable from the terminal window, right? But you want to also do the same thing and you can read the value in the terminal window. You want to do the same thing in your application code, which is also possible to do. So there are two functions. Okay, there are two functions which are available to us. One is called getEnv. So getEnv is where you will provide the environment variable string name, right? The name of the variable will be provided as a string here. So for example, like shell or host, right? This is the value. This is what will read the value of the environment variable. Okay, and then you have the setEnv also, where you will be able to set a new variable as an environment variable. However, remember that the set environment variable you are setting in the C program. So any process that is a child process of this one will have an access to that environment variable. Because remember what I said when we were, when we were considering the environment variable are accessible in the current process and all the child processes. Okay, they are not available in any other process. Local variables are only available in the current process, not even the child process, right? That is the primary difference between the two, right? So so you can actually set an environment variable in your C program, and if you do fork, right, from your C program, that environment variable will be available in the child process. Okay, so that is something that also you can do. So let me run that code again, and okay, so again the output is not very interesting. However, you can see that we are reading the value of the shell environment variable and home environment variable. So if you say echo $shell, you will see that that is the value that comes up. You can say echo $home, then that is the value that comes up, and so on, right? So you are able to read the value of the environment variables or set the environment variables in the C code also. Okay, so this is where we end with the process management. Okay, so this was the last topic I wanted to cover in the process management, and so that is where we end. So if you have any questions about the process management, I can take that, or else we continue. Any questions from anyone? Anything that was not clear to you about the process management? Am I still audible?
Yes, sir.
Okay, just want to make sure that I didn't put you guys to sleep. Okay, all right, so if there are no questions, let me start with next chapter. But as I mentioned earlier, our exam topic will basically stop at this point, right? So we will not consider the ITC, which is the next topic which I am starting for the exam, right? So until process management is what we will do, what will be the syllabus for the exam. Okay, all right. So inter-process communication, right? Now, we recently saw an example that if you want your parent process, right? If you want your parent process to send the data to the child process, the only way that we know so far is by passing that into the command line arguments. Okay. Similarly, if the child process wants to send data back to the parent process, the only way is passing that single integer value in the exit code. And that's about it. We don't have any other mechanism, or we have not learned any other mechanism till now where you can pass a different data types or a large amount of data between your parent and the child process, right? So the point is that why do we need inter-process communication? The reason we need inter-process communication is because you have two processes which does share file descriptors, which does share variables in the read-only mode, meaning that once the variables are created before the fork, right, and you share those variables after the fork, however, the updated value from the one process is not available to another process, right? So even though the variable names are shared, they are really two different variables. So what I'm trying to say is that we don't have a way of communicating, or we didn't learn yet the way of communicating between the processes, right? But we want to do that, and that is what we talk about, the inter-process communication, right? Now, when you use inter-process communication methods, there are primarily two categories. Okay, so it is possible that the examples that we are looking at right now, that we have multiple processes running on the same system. Okay, so same physical computer, which has a common memory, which may have multiple cores, but it has a common memory, right? So basically we call that as a shared memory architecture. Shared memory architecture means that it has a common DRAM, right? And if you write a data into a memory, the other processor can actually read that data from there. So one process can write it into the memory and the other process can read it, right? So we call that as a shared memory architecture, which means that when you have multiple processes running on the same system, you have different ways of doing inter-process communication. So one is called pipe, okay, which is what we are going to learn in this chapter. Signals are another way of communication, inter-process communication for same machine, local machine, and that we are going to study in the next chapter. The third way is actually, I said multiprocessing, but here I mean to say multi-threading, right? So multiprocessing, multi-threading approach, where we use a computer with the same memory, multiple cores, and you are able to communicate using shared variables. Okay, so that is the third type of communication or inter-process communication we can use here. Okay, However, if your processes are running on different machines altogether, they are connected by network, right? So for example, I have my machine, and let's say I want to communicate with one of your machines, one of your laptops, right? So the process is running on your laptop, a process is running on my laptop, and I want to communicate between the two. How do I do that? I have to use something called as message passing interface or socket programming. Now, socket programming, we will consider, we will do the socket programming in this course. However, message passing interface is not something that I normally cover in this course, because this is actually part of distributed programming. It's a advanced topic than this one, right? So if you are interested in that topic, I can definitely discuss about that offline. However, message passing interface is not part of the syllabus in this course. Okay, so we will be basically covering these three areas. Okay, so now we talk about interprocess communication with pipe. Okay, we have used pipe, and you should have a little bit of idea about what the pipe is, but regardless, I'm going to cover that from start, right? So pipe are basically communication mechanism, right, that allows two or more processes to communicate or send information between each other. What it does, it basically takes one process and connects the standard out of that process to the standard input for another process, right? So basically what the pipe does, it basically connects the standard out of one process and it connects the standard input of the another process. So that is why we call it as pipe, right? So you take an output from one process and feed it as an input to the other process. So the example is something like this. Now we have actually, we did several examples. In fact, today itself, okay. So we just saw that you can do env, right, and then pipe, right? So this operator is nothing but a pipe, right? So we are taking an output, the output as a standard output from the env application, which is the env process. So this will have a different process ID, and then I'm doing grep, right, which is a different process. So grep is a different program, env is a different program. So the process ID of env is different, process ID of grep is different. Okay, and then I'm saying grep, let's say home. Okay, so what did he do? Whatever the output that was generated from env, that was sent to the standard output, but instead of going, sending that, data to the standard output, it actually took that data. This pipe operator took that data and sent it as the standard input for the grep. Right, so grep is another process which is running, and it sent that data to the grep, and that data was screened by the grep command to search for the home keyword, right? And home was found only in this one line, and therefore you got this as an output, right? Similarly, we also looked at, let's say, grep Firefox, or we did ps minus ajxf, and then we did pipe, and then we said grep Firefox, right? So when we do that, what does it do? It takes the standard output data from this process, it feeds that data as an input for the grep. That is what the pipe does. Okay, that is what the pipe basically does. So why it is called pipe is, I kind of give an analogy of a water pipe, or whatever pipe generally that you want to consider. You flow the water from the one side in, and then you take the water out from the other side, right? So it's basically a unidirectional pipe. Okay, so let's assume that this is a process which displays some data. So who is the process which displays the user information, that this is the user and what time that user has logged in and so on, right? So it displays that information. And wc is the command which takes the data as an input, and it displays the information about number of lines, right, number of words and number of characters. Okay, so it basically says that whatever the output that was generated by who command, right, or who process has one line. It has one line. It has 5 words: 1, 2, 3, 4, and 5. Right, so it has 5 words. So 5 words are there, and then it has 46 characters. So again, you are connecting the two processes, right, like this, using the pipe command. Okay, so we looked at why we need a pipe command, because as we said, if the child process wants to send the information, which is not just a single integer value, then how do we do it, right? So child process can send larger amount of data. Similarly, parents wants to send also the data which is modified after the child process is created. So it can, if it is a static information which was stored before the fork command, that can be shared with the child. However, when the parents get some information from somewhere and wants to share that data with the child process, how do we do it? For example, let's say you have the parent process which is listening on some network port, right? So you are getting a data from the network, and you want that data to be processed by multiple child processes. So how do you disseminate that data, right? How do you distribute that data? You need some way of communicating between the parent and the child, so that once the data is received, then the parent should be able to distribute it to them, distribute it to the multiple child processes, right? So again, you need something like that, and that is where we use pipes. Okay, so pipe, as you can see, it should have a writer process and it should have a reader process. So again, if we go back to this picture here, right? So this guy is a writer process. So who is sending the data to the pipe, and WC is a reader process, because this is basically reading the data from the pipe, right? So the standard output is the writer of the pipe, and standard input for this guy is the reading or the read side of the pipe, right? So both these processes are running concurrently. Again, you have to keep that in mind, that they are two different processes and two different process IDs. So both of these processes can or will run concurrently, right? It is not that the writer runs and then reader runs, or reader runs first and then writer runs. It's not like that, right? Both processes are separate. Both processes have their own PIDs and they run simultaneously, concurrently. So therefore, it is possible that the writer process is writing fast enough, right? But the reader process is slow. In that case, the pipe can get full. The pipe can get full, right? So if the pipe gets full, then the writer process may have to wait for the pipe to get free a little bit, right? So some reader process has to read the data from the pipe in order to be able to writer process to write the data. Similarly, if the pipe is empty and the reader process is trying to read from the empty pipe, again the reader process will be suspended, because somebody has to write the data. The writer process has to write the data in the pipe. Okay, so again this scenario could happen because again they are two different processes. Okay, somebody has question? What is the width of storage limit? Yeah, I'm coming to that. It's basically 5K size. 5K size buffer. You can see in the next slide itself. Okay, so the pipe is the system call that will be issued when you want to create your own pipe in your C program. And we generally call that as unnamed pipe, because there is no name given to the pipe. There are some operating systems that uses the named pipe, but you don't, most of the time you don't really need the name of the pipe. You can just use pipe as is, and once we look at the example, you will know that why there is no really reason to have the name for the pipe. Okay, so basically, generally speaking, the buffer internally that is used by the Unix-based operating system is approximately 5 kilobytes. Okay, you use the right end of the pipe to write the data using the write system call, So we have seen the write system call for files. We use the same write system call even for the pipe to write the data into the pipe. And you can use the read system call to read the data from the pipe. However, when you write the data, writing will be happening on the right end of the pipe, meaning that it will be writing the data here, right? Whereas when you read the data, it will be reading the data from here. Okay, so that is how the reading and writing will be happening. The process at the end of the completion of the process, meaning that once you're done with the file usage, or sorry, pipe usage, you need to close the file descriptors, right? Like we do with the files, right? So in short, again, we will be using unbuffered IO system calls that we have studied earlier, which is for read, write, and close, in order to use, in order to read, write, and close the pipe. Okay. Now, let me just talk about this picture here so that it is actually very clear to you. See, usually when you use files, normal files, right, the text files or binary files, reading and writing both happens using the same file descriptor, right? Because there is really no difference between reading and writing. You are writing at the same byte, you are reading at the same byte. Okay, and the same file is read and write both, right? So you have a file which is read and write, which allows read and write both at the same byte. However, pipe is slightly different, right? Pipe has two different ends, right? So it has a write end and it has a read end. So one process is going to be reading from the read end, and the other process is going to be writing. So therefore, there are two file descriptors required, one for the write end, one for the read end, for two different processes to use that. Okay, so whichever is the writer process will always be using this file descriptor. So what we have to do is that we have to actually use an array of 2 for the file descriptor, which is then passed as a parameter to the pipe system call. Okay, so pipe system call actually returns you 2 file descriptors, not just one. Your open system call, which is used to open the files, you only get one single file descriptor in return. However, for the pipe system call, you get 2 file descriptors in return. And the file descriptor at index 0 is always going to be used for reading. And file descriptor at index 1 is always going to be used for writing. Okay, so always remember that index 0 is for read, index 1 is for write, and this is always the case. It is fixed. Okay, it is fixed by the operating system. So whichever process is treated as a reader process or considered as a reader process, it only has to use this particular file descriptor. Whichever is the writer process, it only has to consider this as a writing. Now, writer process can actually read the data from the same pipe also, and the reader process can also write the data into the same pipe also. But remember, if both the processes are writing from the same end, and the data that is there in the pipe will be jumbled, right? Meaning that there will be some data from one writer process and there will be some data from the other writer process. So there has to be some demarcation, some indication that says what data is coming from where. Or the other way, other option is that when one process is sending the data, right, from right end and other, let's assume that this is my parent process. Parent process is writing the data and the child process is reading the data. So till all the data from the parent is written and the child has read, you don't want your child process to write the data into the same pipe. Okay, so that is something again you can handle in your application code, in your system programming code, right? So you can say that while parent is writing, child will only be reading, right? And then when child wants to write, parent will not be allowed to write. So something like that you have to do. You have to manage it like that, right? So that's why the pipe are called unidirectional communication. Unidirectional. It is not bidirectional. Okay, because at a time you can only send data from one process to the other. It is not bidirectional. Okay. Okay. Now, whenever operating system implements read and write operation, it does have some conditions that is applicable. So, for example, if the process reads from the pipe whose write end is closed, meaning that the writer process has already closed the write area, right? The write file descriptor. Then the reader process will get a value 0 in return, indicating that there is no data going to be available by the writer, right? Because see, the writer has already closed its end, right? The writer end is already closed, right? So again, if we go back here, if this end is closed, then there is no data that's going to come out over here ever, right? So therefore, the reader process will get 0 in return. If the process reads from the empty pipe, but the writer end is still open, right? So write end is still open, and the reader process is trying to read the data from the pipe, then that process will be put in sleep mode or suspended mode until the new data is available. So that means this read is going to be a blocking read, right? So the process will go into sleep mode. If the process tries to read more bytes from the pipe than that are present, the current content is returned and the number of bytes will be actually read. So for example, process says that I'm going to read 1000 bytes, but the pipe only has 100 bytes. Then all the 100 bytes will be returned back, and the count of the byte, which is 100, will also be returned back. Okay, so these are the conditions for the read operations or the reader process. What are the conditions for the writer process? So for the writer process, we are saying that if the writer process tries to write in the pipe whose read end is already closed, meaning that the reader process says that I'm not going to read anymore from this pipe, and it has already closed the file descriptor for the read side. Okay, in that case, the writer has to fail, because if it is able to write but nobody is going to read, right? So writer process should not be allowed to write also. Okay, so the writer process fails, and the writer process is sent a signal called sig pipe. So again, we will study that when we study signal handling, right? But basically, the writer process will be getting this signal, and eventually the writer process will terminate. Okay, so writer process will be forced to terminate when this signal is sent to the writer process. If the writer process writes fewer bytes to the pipe than the pipe can hold, right? So it means that pipe has more space and process is trying to write less amount of data, then obviously the write will be atomic, meaning that all of that data will go into the pipe. However, if the writer process has more data to be written, then it will have to perform another write for the remaining part of the data. So basically, the write call will tell you that how much data was written into the pipe, and then the pipe actually gets full, right? So then the writer process will know that, okay, I asked to write 100 bytes, but there was only 50 bytes space in the pipe, so therefore I have to wait and I have to issue another write call. Okay, if the pipe call, when you issue a pipe call, if there is not enough space in the memory, right, for the buffer allocation, then the operating system will return you a -1 value. Otherwise, successful pipe call will get a +1 value. Okay. Now this read and write conditions are there, and we are actually going to see how the actual implementation of read and write calls are done in the operating system. But since we are over the time, I'll take that in the next lecture. Because it's going to take probably 10 minutes or so more, right? So, we will basically study how the actual read and write are implemented by the operating system, for the pipe, right? But if you have any questions for the pipe as a general or introductory material, we can take that. Any questions from anyone?
Sir, when we use that symbol for pipe standing line. Do it
Yes.
basically calls the pipe function?
Yeah. Yes. So see, that is the beauty of Unix-based operating system. All the system calls that are accessible to us, right? The operating system also uses the same system calls to internally implement all of these things, all of these functionality. And believe me, at the end of this chapter, using this connect command, I'm actually going to show you exactly how we can implement pipe in our own code. Like I showed you how we can implement pwd command. Similarly, I will show you how to implement a pipe operator in our own code. So the point is that it's a beauty of Unix based operating system. It allows us to use the same functionality that it is using for implementing kernel details. That is one of the primary, see, that is one of the primary reason a lot of people actually do system programming in Unix flavors, right? Windows is not open that much, right? I mean, from the Windows, we may not have a lot of details as to the real implementation details, because it was meant to be used by as a user friendly operating system, right? So Windows is meant to be used as a user friendly operating system, whereas Unix based operating system is more for programmers, more for people like us.
Right, sir.
Any other question? Okay, all right. Thanks everyone. I'll talk to you guys on Thursday.
Hello, sir.
Yeah.
Sir, I was having a small question. Sir, you told that a pipe is like a communication link, right, between the writer process and the reader process.
I'm sorry. Can you come again?
Sir, in one of the slides, you mentioned that a pipe is a communication link.
Yeah.
Sir, what do we mean by a communication link in this context? Hello, sir, you're not audible. Hello, sir. Sir, you're not audible. Hello, is sir audible? Is sir audible? Are present over here.
Sorry, my network went down. So I don't know if you are still there. The person who was asking question.
Yes, yes. Sir.
Okay. So I don't know when did it got disconnected, but basically what I was saying is that the point is that it is one way, or it is a mode of communication, because your child process or parent process can be designated as a writer process, right? And the other process can be designated as a reader process. And so you can actually send the data from the writer process to the reader process using the pipe, and that data can be in the form of string, it can be in the form of structure, anything, right? So even though the parent and the child process are not really sharing the memory, right, they are not really sharing the memory, however the data can be sent from one process to the other. And what I was saying is that if it is not really, you are not able to visualize it right now, don't worry about it, because when we look at the examples, right, the couple of examples that I have, talk unidirectional and talk bidirectional, it will be very clear to you that how actually the process are communicating using pipe.
Okay. Yes. Sir. Yes,
Okay.
sir.
So this is why I never have a lecture without an example, right? I mean, I will never discuss a topic without an example of code, because unless you, I mean, once you look at the code and once you see how it is running, hopefully it will help you better visualize how it is working, right? Because
yes.
with the theory only, it is not very easy to visualize how it is working. Okay.
Yes. Sir. Yes, now it is somewhat clear to me.
Okay. All right.
Thank you,
Okay.
sir. Thank you so much.
Okay. All right. Thanks.